Hi everybody. First thing we want to do today is finish section 6.4. The next topic that we have in this section is rational solutions of polynomials. And by rational we mean fractions, p over q, where p and q are integers. P, q, elements of I. Okay, now on page 472 you have this general form of a polynomial written down. We've written down general forms for specific numbers, 4, 3, 2, 1, 0 as our exponents. And we called our coefficients A, B, C, D. In general, it can be done this way. Here my highest power is n, and I don't know what n is. It's not a specific number. So we say, okay, the nth term, that is the term where x is raised to the power n, we'll call that coefficient a sub n. Then the next term is going to have a power 1 less, so it's going to be n minus 1. So we have x to the power n minus 1, and we'll call that coefficient a sub n minus 1. The next coefficient will be a sub n minus 2, so on and so forth. So you see the 3 dots in the middle there, till you get down to the x term, where your exponent is the invisible 1. So we call that coefficient a sub 1. And then finally we get the constant term, where the power of x is 0, so we don't see x. And we just call this constant coefficient a sub 0. This says that the a sub I are elements of I. That is to say, all these coefficients, we'll just call that the general coefficient, they're a sub I. Elements of I, they're all integers. So if you have a polynomial with all integer coefficients, it turns out there's a simple rule for figuring out what the possibilities are for the rational roots of this equation. They are all these possible combinations, all fractions p over q, where p is an integer that divides the constant coefficient, q is an integer that divides the high order coefficient, a sub n. Now this terminology that I'm using in this form for writing a polynomial, this is stuff you'll see all the time for those of you who are going on to calculus. Let's look at example 4 and see how we can use this information. This is a very long, complicated example. Suppose you're asked to find the solution of this 4th degree equation. 2x to the 4th plus 10x cubed plus 13x squared minus x minus 6 equals 0. Here's one way you can get it done. We'll try to get the rational roots. Once we have the rational roots, we might be able to get the irrational roots. Keep in mind, when I say irrational, I mean they're going to have radical signs in them. And could be a cube root, could be a 4th root. Okay? Right now, we can just use this technique to get the fractions, no radical signs, to get those roots. So all the possibilities are going to be these combinations of p and q. Now we see in our example, p, the number, p is the all possibilities of numbers that divide, of integers that divide a sub 0. Here a sub 0 is negative 6. So, well, okay. I can't say that they equal these numbers. I can say they divide. So there you go. There's a new mathematical symbol you haven't seen before. P divides negative 6. Therefore, P is either going to be plus or minus 1, or plus or minus 2, or plus or minus 3, or plus or minus 6. No other possibilities for p. But that's enough. I mean, that's 8 integers right there that we have to check out combinations of. Q has to divide 2, right? That lead coefficient. So that means possibilities are plus or minus 1, plus or minus 2. So we have to figure out what's all the possible combinations between this list of 8 integers up here and this list of 4 more integers down here. That's a lot of possibilities. All right. Let's look at and list all the possible P over Q combinations we can get. First of all, when Q is equal to plus or minus 1. Okay, that's pretty easy because I can look at my list of possibilities for P and say, well, all right, when Q is plus or minus 1, I just have these same possibilities. Whether I divide by 1 or I divide by -1, I'm always going to get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. All right, so that was pretty easy. Now what about when Q is plus or minus 2? We work our way down the list, so we get plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 6 over 2. And that's all our possibilities. Now usually you're going to get some repeats in there. Like plus or minus 2 over 2, that's just the same as plus or minus 1. So we can cross that out. And plus or minus 6 over 2, that works out to be an integer also. That's plus or minus 3. So we can get rid of those two. Now, in this modern day and age of graphing calculators, we can use the graph of the function to eliminate some possibilities. Look at figure 6.34. If you were to take this polynomial in x and set it equal to y, you would have a graph that looks like this. Okay, whoops, there's a boo-boo. We have one more hump in there. This is a 4th degree polynomial, so yeah, unless you have lots of pieces missing, and we don't have pieces missing, you're going to get 4 humps. Right, so it comes in from positive territory here, and it goes out to positive territory here. All right. What does this tell you? It tells you a couple things. First of all, it looks like -1 and -2 are roots of the polynomial. And we see -1 and -2 are listed as possibilities. So that looks pretty promising. I suspect they're roots, and we're going to have to check that. The second thing it tells you is that the x-intercepts between 2 and 3 must be irrational, right? There is an x-intercept there, but it must look like that with a radical sign in there, raised to some power. We'll see what happens. Similarly, between 0 and 1, another x-intercept must be irrational. Can't be a fraction. Must have a radical sign in it. Now you could say, oh, well, wait a minute, one of our possibilities is +1/2, and this is going this intercept here is happening between 0 and +1, so I think I'll try it out. Well, you could. And it's not going to work. Now you could try it out just by plugging 1/2 in there. Get some fractions to deal with. It's kind of a slow, tedious way to go. What works a lot better is if we use our new tool, synthetic division. Let me just get a little more space there. And let's try out x equals -1. So I'm going to try -1. That's a rational possibility, possibility for a rational root. And the graph kind of indicates that it probably is. So let's divide using synthetic division. We'll divide -1 into this polynomial. So my coefficients are 2, 10, 13, -1, -6. Bring down the 2. 2 times -1 gives me -2. Add them up. 8. 8 times -1 gives me -8. Add them up. 5. 5 times -1 gives me -5. Add them up. -6. -6 times 1 gives me +6. I get a 0. So that checks out. -1 is, in fact, a root of this equation. And -1 is where that x-intercept is actually occurring. The other possibility is -2. So I set up that synthetic division. Bring down the 2. 2 times -2 is -4. Add them up. 6. 6 times -2 is -12. Add them up. 1. 1 times -2, -2. Add them up. -3. -3 times -2, +6. Add them up. 0. So that one checks out also. Oh! I forgot to teach you this, though. I did figure out that -2 works, fine, but I could have done better than that. I could have made the problem simpler. And the result of doing this synthetic division, I could have made it more useful. This tells me that my next synthetic division can look like this, right? What I have figured out here is that, and where am I going to scrunch this in? I'll have to go down here. Don't forget, when you do a synthetic division like this and it checks out and you get 0, this tells you that your polynomial has been factored, like this. Since -1 is a root, x plus 1 is a factor. And what's the remaining quotient there? -2 times x to 1 less power, x cubed, minus 8 times x squared, minus 5x plus 6. Right? You have factored that polynomial into that. And that, of course, is a very useful piece of information, and we're going to use it. That's a +5, sorry about that. And that's a, oops. I should be looking at my resulting line here, my answer. I was looking at this line, so I have all my signs reversed. Okay? This is your quotient polynomial. Right? That's what results. So this whole synthetic division here shows me that my original polynomial can be factored like this. So, to see if negative 2 is a root, I can just divide it into this one, underlined in green here. So that's what I'll do. So less numbers to deal with, and it'll give me another factorization. When I'm done here, right, if negative 2 is truly a root, I will be factoring out x plus 2 as my next factor, and I'll have some polynomial here, and that polynomial will have one less degree, so I'll be down to an x squared as my high order term. In other words, a quadratic expression, and we have a formula that solves all quadratic expressions, right? Quadratic equations. It's the quadratic formula. All right, so I do this synthetic division, bring down the 2 to the negative 12. That seems too big. Did I make a mistake already? Yes. 2 times this gives me a negative 4. And, oh, I see. Got my signs reversed here. So I get a positive 4. 4 times negative 2 gives me negative 8. Negative 3, 6, 0. Okay. So I see the resulting quotient is 2x squared plus 4x minus 3. All right, now we're making some serious progress. I know that this equals this. So I see my 2 roots there. I expect to see 2 more out of here. The one that's there and the one that's there. So it looks like one of my answers is going to be some number close to positive 1, but not all the way there, a little smaller. And the other number will be between negative 2 and negative 3. That's what I expect to see looking at the graph. So we're going to have to clear out some space here. And we'll use the quadratic formula. A is 2, B is 4. C is negative 3. All over 2 times A. Does everybody see how I go from this quadratic expression here, right? X squared term, X term, constant term. Plug them into the formula. Okay. And I arrive there. This can be simplified a bit, right? 2 goes into that 2 times, 2 goes into that. I'm sorry, 2 goes into that once, 2 goes into that 2 times. 2. So this is the same as negative 2 plus the square root of 10 over 2. Okay, so to recap the strategy, we found the possibilities for rational roots. So we figured out what the rational roots were. Negative 1, negative 2.